this exercise, I'll try to show the effect of CFL discussed in the previous lecture. For that, we'll look at the diffusion problem with the Fick's second law. So we have a rod of length L total, and there is an initial distribution of concentration in this rod. And at the right end, we apply some concentration, and then we perform simulations to see the evolution of concentration profile in this rod. And we would like to analyze the influence of spatial and temporal discretization on a diffusion in this rod. So we'll first try a few elements, and then we can discretize this rod in more elements. So how do we do it? First of all, let's import the packages we'll use later. Import NumPy and import matplotlib for plotting the results. Now, if the total length is L and if we discretize our rod in n elements, then the element length of each element can be found as L total over n. So let's write it down. The total length L, let it be 1. Let's number of elements, truss elements, we discretize it, let it be 41. And so it means the length of each element is equal to total L over 41. We also have to define the diffusion coefficient, which describes the transport properties along the rod. So let's define it as D, 0.01. The element mass matrix of a 1D truss with linear shape functions can be found as this one. So let's write it down. The element stiffness matrix of the 1D truss with the linear shape functions is written like that. However, here at the top we have our diffusivity D, which describes the transport properties of our 1D truss. So now we have to determine the number of degrees of freedom. So if we have n elements, then we'll have n plus 1 degrees of freedom. So for example, in this case, if we have 2 elements, we'll have 3 degrees of freedom. If we have 5 elements, we'll have 5 degrees of freedom. Now we have to assemble the global mass and stiffness matrices. In order to do it, first we have our global matrix. For example, with 4 elements, we'll have here then 5 degrees of freedom from 0 to 4, like it's shown here. And what we have to do here, we have to just take the local stiffness matrices and put them in a diagonal in a global stiffness matrix, where these diagonal elements will overlap, so it means we'll have to sum them up. So let's first initialize the global matrix K and global matrix M. It will have sizes end of times end of. Now we will look through all the elements and insert components of each local element matrix into our global matrix. So n here is the number of elements, and here we add to the global stiffness matrix the components of the element matrix. We do the same also for the mass matrix. The discrete form of diffusion equation can be written as follows: m times c dot, the time derivative of concentration, and plus k times c is equal to f external. F external, it may be sink or surge term. So now we have to bring this term on the right hand side, obtain this equation, and then if we write c dot as cn plus 1 minus cn over delta t, we obtain this equation, and then just like bring all the terms corresponding to the time step n to the right hand side, and then we can obtain the concentration at time step n plus 1. So m is the mass matrix, Cn is concentration at time step n, delta T is the time step size. Let's initialize the vectors for the concentration and external load, and we assume that the initial concentration within the road is 0 and initial external loads are also 0. We apply the concentration at the right end of the road here. So if it will be our last degree of freedom, and the last degree of freedom can be written as -1 in Python. So write C at -1. And let's give it the value 10. Now we have to define the total time, which we calculate, and a time step size. And we have to initialize array to store the solution which we obtain at each time step. So here in the first instance we save the initial concentration. We have to invert the mass matrix M, so we do it once before we start the algorithm in order to save time. Now we have to loop through all the time steps and update concentrations at each time step. For that we will use the for loop. The concentration at the right end of the road in each time step we keep it the value equal to 10, and Cn plus 1 can be written according to this formula here. Now we have to update the C, and we store the values at each time step. After the calculation has finished, now we can plot the results. In this case, we will be plotting the concentration profile, so we'll plot the concentration along the length of the road. So x-axis is the road length, y-axis is the concentration. So we see at the right end we keep the concentration constant equal to 10, and here we have still concentration equal to 0. However, we see here an oscillations. Now we calculated it for the time 1 second. If we now calculate it for 1.5, if we continue performing the simulation in time, the solution blows up, and it means we cannot continue performing the further calculation. Let's look again at the solution, at our solution after 0.5 seconds. And now if we reduce the size of the elements even more, so for example instead of 41, if we use 51 elements, we said situation gets even worse. This is 10 to the power of 14, and our solution blows up. So in order to improve it, we also have to reduce the time step. We see that the solution is stable, so the smaller the mesh size, the smaller must be the time step size.